Welcome to The Deep Dive, the show where we cut through the noise of cutting-edge research and articles, distill it down, and deliver the most important insights straight to you.
Glad to be here.
Today we're plunging into a topic that's been, well, electrifying the AI community. The Qwen3 model family.
Yeah, things are moving incredibly fast.
The pace of innovation in large language models is just relentless, isn't it? And specifically, the Qwen3 coder variant is generating some serious buzz because it brings truly state-of-the-art capabilities right into the hands of more users, especially with its laser focus on what's called agentic coding and its incredible efficiency.
It's a really compelling development. What's truly insightful here, I think, is how Qwen3 aims to bridge that persistent gap between, theoretical high benchmark performance and actual practical accessible deployment.
Right, getting it out of the lab.
Exactly. For many, this isn't just another model. It promises to redefine what's achievable on more modest hardware while simultaneously pushing the boundaries of what these models can do.
In terms of complex reasoning and action.
Precisely. Reasoning and action, it's a significant step towards, democratizing advanced AI capabilities.
Absolutely. And that idea of democratizing advanced AI is really at the heart of our mission for this deep dive. We're going to take you on a comprehensive tour, unpacking the intricate technical details, exploring the broader implications of these advancements to the AI landscape, and maybe even revealing some surprising facts about the Qwen3 coder models.
Sounds good.
Consider this your shortcut to being well-informed, ensuring you understand exactly what makes these models so significant right now. We're focusing squarely on the technical architecture and the operational improvements, so let's jump right in.
Let's do it.
Okay, let's unpack this new frontier in LLMs, the Qwen3 family. Now, this isn't just one model, is it?
No, not at all. It's an entire series.
A whole family.
Exactly, spanning from incredibly compact versions at 0.6 billion parameters,
Oh, we're tiny.
all the way up to a truly colossal 235 billion parameters.
That's a massive spectrum for developers to choose from, depending on their compute and their specific task.
It truly is a strategic range. This diverse offering allows for everything from deployment on edge devices, maybe your smartphone eventually, to large-scale data center applications for the really heavy-duty tasks.
Right.
But the core innovation, I think, the thing that permeates the entire Qwen3 series, regardless of size, is its seamless integration of two distinct operating modes within a single model.
Okay, two modes.
Yeah, a thinking mode for complex, multi-step reasoning tasks, and a non-thinking mode for rapid, direct, context-driven responses.
That's a transformative leap right there.
Okay.
So you're telling me users don't need to juggle between different specialized models, say one for deep reasoning and another for quick chat.
Exactly.
It's all built into one unified framework.
It is. That sounds like it eliminates a huge amount of friction for developers.
Yep.
Precisely. This unified framework eliminates the cumbersome need for users to switch between entirely different models, offering, unparalleled flexibility within a single instance.
Okay.
And building on that, they've introduced a truly novel feature called the thinking budget mechanism.
Thinking budget, what's that?
This isn't just a clever label. It allows you to adaptively allocate computational resources during inference.
Ah, so you control the effort.
You got it, giving you fine-grained control over the model's reasoning effort and, crucially, balancing the latency of a response with its performance depth.
So you can sort of dial it up or down?
You can essentially tell the model, think this hard, but don't spend more than X tokens doing it.
That level of control sounds incredibly useful for developers. You can decide how much internal brainpower you want the model to expend, depending on the task's complexity or your latency requirements.
Exactly.
Are there any unexpected complexities or, trade-offs that come with that kind of fine-grained tuning?
Well, the primary trade-off is indeed between speed and depth.
Right.
Makes sense. While the control is powerful, optimizing it for every unique scenario will probably require some experimentation from the user.
Good.
However, the design inherently helps manage this, allowing coherent answers even if the budget is exhausted, which is quite clever.
That is clever.
And of course, the open source release under the Apache 2.0 license is a significant boon for the entire AI community.
Huge, yeah.
It means researchers and developers everywhere can inspect, modify, and build upon it, accelerating progress and fostering an ecosystem of innovation.
Indeed. It strongly promotes broader research and community-driven innovation in the AI space. And what also stands out dramatically is its vastly expanded multilingual capabilities.
Oh yeah, the language support.
Qwen3 now supports an impressive 119 languages and dialects.
119, that's a lot.
That's a threefold increase from the previous Qwen 2.5, which supported 29. This dramatically broadens its global applicability, reaching communities that might have been underserved by prior models.
A truly impressive jump in linguistic coverage. It means these models aren't just powerful, they're globally accessible, which is a massive step for democratizing advanced AI across diverse user bases.
Okay, so let's zero in on the star of today's deep dive. The Qwen3 Coder 30B A3B Instruct variant. That's a mouthful.
It is.
That A3B suffix isn't just random letters, is it? What does it signify, and why is it so important for understanding this model's breakthrough efficiency?
You're right. The A3B suffix is absolutely key here. It stands for active params 3B.
Yeah, active params 3B.
Okay. And it immediately tells us we're looking at a mixture of experts, or MOE, architecture.
Right, MOE. We hear that a lot lately.
We do. And the profound insight here is how Qwen3's MOE architecture isn't just making AI faster, it's fundamentally redefining the economic and hardware barriers for deploying advanced AI locally.
How so?
Out of a total of 30.5 billion parameters in the model, which is still pretty big.
Yeah, 30 billion.
Only a lean 3.3 billion are actually activated for any given token during inference.
Okay, so it has this vast knowledge base, this 30 billion parameter potential, but it's only activating a small, specialized part of it for any single operation.
Exactly.
That sounds like a brilliant way to optimize for speed while still retaining a large overall capacity.
Is that why users are praising its light speed inference?
Precisely. This MOE design is genuinely a game changer because it directly contributes to its light speed inference and overall efficiency. Users are already reporting lightning-quick speeds, even on consumer-grade hardware.
We'll get to those speed numbers later, I bet.
Oh, yes. This efficiency allows it to achieve significant performance in specialized areas like agentic coding, where it can interact with tools and environments.
The agent stuff.
Right. And agentic browser use and other foundational coding tasks. It proves that you don't always need to activate a massive number of parameters to get top-tier results.
It's about smart activation, not just sheer size.
You nailed it. Smart activation. That's fantastic. It means high performance isn't locked behind super expensive compute, which opens up so many possibilities. What about its ability to handle truly vast amounts of information? Especially for complex coding projects that span multiple files or even entire repositories.
Context length. That's where its long context capabilities truly shine. It has native support for an impressive 256,144 tokens.
250,000 tokens. That's already huge.
It is, but it can be extended even further, up to a staggering 1 million tokens, using techniques like Yarn.
1 million tokens. Wow.
And this isn't just a bigger input window. It's specifically optimized for repository scale understanding and coding tasks.
Okay, so tailored for code.
Exactly. Imagine analyzing an entire code base, a massive pull request, or even a detailed software specification. This model can ingest all that information to provide contextually relevant suggestions, identify bugs, or generate new features.
So it's not just good at generating isolated lines of code, it can actually understand a whole project's architecture and context.
That's the goal.
That's absolutely crucial for real-world software development, where context is king. And you mentioned agentic coding. How does it support that? And with what specific platforms or tools?
It robustly supports various coding platforms, including Qwen Code and Selenium. What's particularly noteworthy is its specially designed function call format.
Function calls, right. Tool use.
Which significantly enhances its agentic capabilities. This means the model isn't just about generating lines of code. It's about enabling the model to interact with its environment, call external tools like APIs, execute actions, and interpret results.
Okay, so it can do things.
Yes. This is a significant step towards more autonomous AI agents in software engineering, where the AI can proactively contribute to complex tasks rather than just passively decorate text.
Fascinating. And it sounds like a lot of thought has gone into making it not just smart, but actionable.
Definitely.
Now let's go even deeper and explore the intricate architectural and training innovations that make Qwen3 possible. This is where the real engineering wizardry comes into play.
All right, under the hood we go.
So let's dive into the guts of Qwen3, starting with its core architectural components. First off, it's categorized as a causal language model, right?
That's correct.
Yeah.
Which means it generates text sequentially, predicting the next token based on the previous ones. That's a standard foundational approach for LLMs.
Pretty standard stuff.
It is. It's fundamental to how these models predict and generate. The Qwen3's architecture largely builds upon its highly successful predecessor, Qwen 2.5,
Okay, building on success.
incorporating well-established and incredibly effective components. We're talking about things like grouped query attention, or GQA,
GQA.
which helps make attention mechanisms more efficient. SWELU, an activation function for the feed-forward networks, rotary positional embeddings, ROPE for robustly handling positional information, especially with pre-normalization, and RMS norm, a normalization technique to ensure stable training.
A lot of proven techniques.
These are all widely adopted best practices in modern high-performance LLM design. They're not reinventing the wheel on those fundamental blocks.
Okay, so building on a very solid foundation. Are there any specific refinements or subtle changes from Qwen 2.5 that are particularly important for its performance or perhaps even more critically for its stability during such massive training runs?
Yes, there are a couple of crucial refinements that warrant specific mention.
Sure.
The Qwen team removed the QKV bias from Qwen 2.
QKV bias. Gone. Why?
Well, it can sometimes lead to instability or make training unpredictable. Imagine a slightly blurry lens on a camera. Removing that bias helps sharpen the focus, make things more stable.
Makes sense.
And they introduced QK norm to the attention mechanism.
QK norm. What does that do?
Think of QK norm as a very precise calibration to the model's attention lens. It ensures it stays focused and learns smoothly, even when processing vast amounts of data.
So more stability tweaks.
Both of these changes are crucial for ensuring stable training in Qwen 3, especially at its immense scale. These might seem like minor tweaks, but they can have profound effects on how well a model learns and converges without, going off the rails.
That makes perfect sense. Stable training is paramount when you're dealing with trillions of tokens and billions of parameters. Now let's get into the granular details of the Qwen3 30B A3B MOE architecture. How does it manage its experts, and what makes its setup unique?
Right, the MOE specifics. This is where it gets really interesting and highlights its unique design. The 30B A3B MOE model features 48 layers, which is quite deep.
48 layers, okay.
For its grouped query attention, it has 32 attention heads for queries, Q, and 4 for key value, KV.
32 and 4. That asymmetry helps efficiency, right?
Correct. It contributes to its efficiencies. Critically, it incorporates a total of 128 experts.
128 experts.
But here's the key. Only 8 experts are activated per token.
Only 8 out of 128.
Right. That means for any given piece of information, only a small, specialized subset of its overall knowledge is brought to bear, making it incredibly fast.
Okay.
And a fascinating detail and a clear departure from Qwen 2.5 MOE is the explicit exclusion of shared expert.
No shared experts at all. It's quite a design choice.
The thinking seems to be that the explicit exclusion encourages a more distinct and efficient specialization among the individual experts.
Forces them to stand on their own.
Kind of. It forces each expert to become truly proficient in its domain without relying on a common fallback.
Okay, but how do they ensure these experts specialize properly without that shared guidance and avoid some experts doing all the work?
Good question. To facilitate this specialization and improve overall model efficiency, they employ a technique called global batch load balancing loss during training.
Load balancing loss.
Oh.
Sounds like traffic control.
It acts very much like a smart traffic controller, yeah. It helps distribute the workload evenly across the experts during training.
Oh, okay.
It prevents some experts from becoming overused while others remain underutilized, thereby maximizing the benefits of the MOE architecture by ensuring all its brains are contributing effectively.
So it's actively nudging the experts to find their unique niches and share the cognitive load. Smart. And finally, what about the tokenizer? That's always a critical component for how a model understands and processes language.
Right, the tokenizer. The Qwen models utilize Qwen's own tokenizer, which implements byte-level byte pair encoding, or BBPE.
BBP?
And it boasts a massive vocabulary size of 151,669.
Whoa, that's a big vocab.
It is. This broad vocabulary, combined with the byte-level encoding, allows it to handle a wide range of characters and languages efficiently, from common scripts to more complex ones.
Which helps with that huge language support we talked about.
Exactly. It contributes directly to its strong multilingual capabilities. It means it can parse a lot of different linguistic structures without running into too many unknown words or characters.
That's a thorough breakdown of the components. It sounds like they've refined a lot of the standard techniques
Yeah.
and added some very specific Mo innovations. How do they actually assemble all those sophisticated pieces and infuse them with intelligence? That brings us to the fascinating multi-stage training process. This is truly the blueprint for its intelligence, isn't it?
Indeed. The training process for Qwen3 is a meticulous, multi-stage endeavor, emphasizing both sheer scale and an incredible diversity of data. It's a carefully choreographed symphony of learning.
When you say scale, what kind of mind-boggling numbers are we talking about for the pre-training data?
We're talking about an enormous data set of approximately 36 trillion tokens.
The 36 trillion.
Trillion. And this isn't just a big number, it covers that expanded range of 119 languages and dialects.
Right.
To truly put that into perspective, it represents a doubling of tokens and a threefold increase in language coverage compared to its predecessor, Qwen 2.5.
Double the tokens, triple the languages. That's immense.
This massive scale ensures a broad understanding of world knowledge, general reasoning, and linguistic nuances across a vast global footprint.
Wow. Doubling tokens and tripling languages is a monumental undertaking.
Yeah.
How did they even begin to curate such a vast and diverse data set without just, endless web scraping or ending up with low-quality junk?
That's the key question. It involved truly innovative data sourcing methods, not just scraping.
Like what?
For instance, they leveraged the Qwen 2.5 VL model, that's their vision language model,
Okay.
for high-quality text extraction from extensive PDF documents. Think about how much structured, curated knowledge is locked away in PDFs, academic papers, textbooks, technical manuals, legal documents.
Right. Tons of good stuff in PDFs.
Extracting that cleanly and accurately is no small feat. Additionally, they employed Qwen 2.5 math and a Qwen 2.5 coder to synthesize trillions of highly domain-specific tokens.
Synthesize, so generate data.
Exactly. This means they weren't just scraping, they were generating high-quality, targeted data, including textbook-style explanations, complex question-answering formats, detailed instructions, and vast amounts of code snippets.
Using their older models to make training data for the new one.
Precisely. This approach ensures the model isn't just learning from general text, but from highly relevant, high-quality, domain-specific examples that teach it how to reason and code.
That's a really ingenious approach. It feels like a form of self-improvement for the AI ecosystem itself, doesn't it?
It really does, a continuous refinement loop.
So how do these massive data sets feed into the actual pre-training process? What are these 3 stages you mentioned, and what's the purpose of each?
Okay, the pre-training is divided into 3 distinct stages, each building on the last. Stage 1, the general stage, or S1, is the foundational phase.
Laying the groundwork.
Right. All Qwen3 models are trained on over 30 trillion tokens with a sequence length of 4,096 tokens. The goal here is to establish a strong, broad foundation of general language proficiency and world knowledge across all 119 supported languages. It's about building a robust general-purpose understanding before specializing.
And after that broad foundation, what's next? Do they then sharpen its focus?
Exactly. Stage 2, the reasoning stage, or S2, does precisely that. It focuses intensely on enhancing reasoning abilities.
Now.
During this phase, the pre-training corpus is optimized to include a significantly higher proportion of STEM, science, technology, engineering, mathematics.
STEM, coding, reasoning.
Coding, general reasoning, and synthetic data, approximately 5 trillion high-quality tokens from those specific domains.
So more focused data.
And they also accelerate the learning rate decay during this phase, which suggests a more rapid, targeted specialization rather than continued, broad exploration. It's about sharpening its logical and problem-solving skills, getting it ready for the complex tasks it will face.
So S1 is broad knowledge. S2 is focused reasoning. What about long context? That's a huge, crucial theme in recent LLM advancements, especially for coding.
That brings us to stage 3, the long context stage. This is the final pre-training stage.
Okay.
Here, models are trained on hundreds of billions of tokens with an extended sequence length of 32,768 tokens.
32K sequence length in training.
Yes, and this stage explicitly incorporates advanced techniques to push the context window even further during inference. They increase the base frequency of rotary positional embeddings, ROPE, using something called the ABF technique,
Okay.
and introduce yarn, yet another rope-in, and dual chunk attention, DCA.
Lots of acronyms there.
Ha, yes. Think of these like a sophisticated indexing and memory management system for a colossal digital library. These methods allow the model to efficiently jump to and understand context across hundreds of thousands, even millions of tokens, without getting lost or overwhelmed or losing coherence.
Giving it that potential million-token context window we talked about.
Exactly. Aiming for that remarkable fourfold increase in sequence length capacity during inference compared to training.
Wow. A fourfold increase is massive. This is where we start seeing the ability to ingest entire code repositories or lengthy legal documents and truly understand their entire scope. But pre-training is only half the story, isn't it?
That's right.
What about the post-training, where they align it and fine-tune its behavior for specific tasks and, crucially, for its thinking capabilities?
Correct. The post-training process is equally sophisticated, maybe even more so. It comprises 4 stages and incorporates a powerful strong-to-weak distillation pipeline.
4 more stages plus distillation. Okay.
It's designed with 2 core intertwined objectives: thinking control and strong-to-weak distillation.
Let's break those down. Thinking control sounds like managing those dynamic modes we discussed earlier, the thinking versus non-thinking.
Exactly. Thinking control is precisely about managing the activation and behavior of the non-thinking versus thinking modes, and also controlling that token budget within the thinking mode.
Okay. And the other objective, strong to weak distillation.
This one is particularly clever and efficient. It optimizes post-training for lightweight models, the smaller ones in the family,
Right.
by leveraging knowledge from larger, more capable models, the teachers.
Knowledge transfer.
Right. This means smaller models can achieve near flagship performance without needing the same massive training runs, making them highly accessible and efficient.
That's a huge efficiency gain for deployment.
Yes.
So walk us through these 4 distinct post-training stages for the flagship models first. What's stage 1?
The first stage is long caught cold start. Caught meaning chain of thought.
Okay, long chain of thought, cold start.
This involves curating a comprehensive dataset of challenging math, code, logical reasoning, and general STEM problems, each meticulously paired with verified answers.
High-quality problems and answers.
And it's a rigorous process with 2 phases of filtering. Query filtering, which removes easily verifiable or multi-sub-question queries, ensuring only complex problems remain.
Filtering the easy stuff out.
Then, response filtering ensures high-quality, non-repetitive, consistent responses that avoid guesswork or language mixing. The objective here is to instill foundational reasoning patterns and robust problem-solving processes.
Like teaching it how to think.
Setting the stage for deeper, more sophisticated learning without over-optimizing for immediate superficial performance.
So it's about making sure the model learns how to think through problems, not just memorizing answers.
Yeah.
What happens in the second stage? Does it get to apply those foundational reasoning patterns?
It does, but with a twist. Stage 2 is reasoning RL, or reinforcement learning.
RL for reasoning.
This stage uses 3,995 challenging query verifier pairs that were not seen in the cold start phase. So they are truly novel problems for the model.
Your challenges.
They apply GRPO, generalized reinforcement learning with policy optimization. This is essentially a sophisticated coaching method. The model learns through trial and error, getting precise feedback to continually refine its problem-solving strategies.
Like training with feedback.
Exactly. Key strategies here include using a large batch size, a high number of rollouts per query, off-policy training for sample efficiency, and entropy control to balance exploration of new solutions with exploitation of known good ones.
Balancing trying new things versus sticking with what works.
Right, and the results are quite tangible. For instance, the AMY24 score, that math competition benchmark, the score of the Qwen3 235B A22B model increased significantly from 70.1 to 85.1 over just 170 RL training steps.
Wow, that's a big jump in score from just 170 steps. Shows how potent targeted reinforcement learning can be for specific skills like mathematical reasoning.
It really does.
What about the thinking mode fusion we talked about earlier? How does that dynamic switching behavior get integrated?
That's stage 3, and it's a critical innovation. This stage integrates the non-thinking capabilities into the already reasoning-capable model through continual supervised fine-tuning, or SFT.
Okay, SFT for fusion.
The SFT dataset thoughtfully combines both thinking and non-thinking data generated via rejection sampling and careful curation, respectively. This teaches the model to handle both types of requests seamlessly within the one model.
And this is where the think and nothing flags come in, right? How did they manage to get a single model to do both so effectively without needing to, physically swap out parts of the model.
This stage features a very clever and innovative chat template design. They introduce those think and nothing flags right within user queries or system messages.
Simple flags.
This allows the model to dynamically switch its internal thinking process on the fly. Even in non-thinking mode, an empty thinking block is conceptually retained in the assistant's response.
Huh. An empty block.
Yeah, just to ensure internal format consistency. It means the model keeps its internal structure even when it's not explicitly thinking out loud, so to speak.
Interesting detail.
And a truly fascinating outcome here is the emergent thinking budget control we discussed. The model naturally handles intermediate cases, generating coherent responses based on incomplete thinking if a user-defined thinking budget is met.
It learned that itself.
It appears to be an implicit capability that arises from the training, not something explicitly hard-coded. It learned to be flexible with its reasoning.
That's a beautiful example of emergent behavior in AI, the model implicitly learning a nuanced control mechanism. What's the final stage of post-training stage 4? How does it bring everything together?
Stage 4 is general RL, which aims to broadly enhance the model's capabilities and stability across diverse scenarios, polish and alignment.
Okay, broad enhancement.
This involves a sophisticated reward system covering over 20 distinct tasks, each with customized scoring criteria. These target instruction following, format adherence, preference alignment, and advanced agent ability.
Agent ability again.
Including multi-turn interactions with real environment feedback.
Wow, feedback from real environments.
Yeah. There are 3 types of rewards used: rule-based, model-based with reference answers, and model-based without reference answers, which are trained on human preference data to capture subjective preferences.
So a mix of objective and subjective feedback.
Exactly. This holistic approach ensures the model is well-aligned and robust across a wide array of applications.
That's a truly comprehensive approach to alignment and behavior shaping. And then there's the strong to weak distillation pipeline for smaller models, which sounds like an efficiency masterclass. How does that work? And what makes it so incredibly efficient?
Right, the distillation. This pipeline is specifically designed to optimize lightweight models, ranging from the very compact 0.6 billion to 14 billion dense models, and notably our focus model, the 30D A3B MOE.
Okay.
It's divided into 2 primary phases: off-policy distillation and on-policy distillation.
Off-policy and on-policy.
In the off-policy phase, they combine outputs of larger teacher models like the Qwen3 32B or the flagship Qwen3 235B A22B to impart basic reasoning and mode-switching skills to the smaller student models, kind of like learning by example.
Learning from the big siblings.
Then, in the on-policy phase, the student model generates sequences and is fine-tuned by aligning its internal logic, or logits, with the teacher model to minimize KL divergence.
Aligning the internal thinking.
Essentially, yes, teaching the smaller model to think and respond like the larger, more powerful one.
And this is much faster.
This process is remarkably efficient, requiring only about 1/110th of the GPU hours compared to direct reinforcement learning on the student model. And it's highly effective in improving exploration and reasoning potential in the smaller models.
So it's like a highly efficient knowledge transfer from the big brains to the smaller ones, optimizing their capabilities without the full, costly training.
That's a great way to put it.
That's incredibly smart. This multi-stage process, combined with the architectural choices, clearly lays the groundwork for the impressive performance we're seeing. Let's talk about that performance now and what it actually does in the real world.
Right, let's see the results.
Okay, so with all that complex architecture and meticulous multi-stage training, what does Qwen3 actually do? Let's unpack its agentic coding prowess first, because that's a key highlight.
Absolutely. Qwen3 Coder truly excels in its tool calling capabilities. This is a significant aspect of agentic behavior.
Right, using tools.
The ability for the model to recognize when it needs an external function or tool and then to correctly invoke it. Users can simply define and leverage external tools like the square the number function example provided in the source material.
It's a simple example, but powerful.
And the model understands how to use it within its reasoning process, executing actions, not just generating text.
So it's not just generating code, it's generating actions that interact with an environment or a toolkit, which is a big step towards autonomous agents.
Does it play nicely with existing developer tools and ecosystems?
It seems to. It integrates seamlessly with OpenAI API-compatible endpoints for tool usage.
Okay, OpenAI compatibility is good.
Showcasing its flexibility within existing developer ecosystems. Beyond that, it has specialized tools and integrations like Qwen code.
Qwen code.
Yeah, it's a command line interface tool forked from Gemini code and specifically adapted for Qwen3 coder. It also directly supports Claude Code and Sline, both accessible via NPM packages.
So several ways to use its coding abilities.
This broad compatibility means developers have multiple robust avenues to leverage its agentic capabilities without overhauling their existing workflows.
That's a strong endorsement for practical real-world use. What kind of applications can it handle beyond just simple function calls? Give us some concrete, perhaps even surprising examples of its diverse capabilities. Well, its diverse applications in coding and simulation tasks are quite impressive and cover a wide spectrum. We're seeing examples from highly complex physics-based chimney demolition simulations.
Chimney demolition, seriously.
Seriously. To more standard web development for online bookstores, and even creating engaging games like Flappy Bird, a bouncing ball in a hypercube, or a detailed solar system simulation.
Wow, from physics sims to Flappy Bird.
The breadth of these examples underscores its versatility as a coding agent capable of handling a variety of abstract and practical challenges.
And the user feedback seems to back this up consistently, with some community members noting, all Qwen models are good at using tools, even the smaller 4B one.
Yeah, that consistency is interesting.
It's a consistent strength across the family, which is great to hear. But how does it stack up against other leading models in formal benchmarks? Is it just good for its size, or is it truly competitive?
On overall performance, the flagship Qwen3 235B A22B model demonstrates state-of-the-art results among open-source models.
Soda for open source.
Yes, in both thinking and non-thinking modes. And this isn't just about being good for an open-source model. It's highly competitive with leading closed-source models like OpenAI o1, Gemini 2.5 Pro, and GPT-4o.
Closing the gap with the big players.
Significantly narrowing that performance gap, yeah. This suggests it's genuinely competing at the top tier of LLMs, regardless of its open source status.
That's a bold claim, especially against the proprietary giants. Where does it specifically shine beyond just overall performance?
It particularly excels in coding, mathematics, and agent-related tasks.
Code, math, agents. Makes sense given the training focus.
Exactly. For instance, it achieved impressive scores like 85.7 on AIME 24, that challenging math competition.
85.7 is very high for AIM.
It is. 70.7 on LiveCodeBench v5, a real-world coding benchmark. A Codeforces rating of 2056, which places it in the 98.2 percentile among competitive programmers.
Wow, 98th percentile coder.
And 70.8 on BFCL v3, another critical agentic benchmark. These are robust indicators of its deep problem-solving and code generation capabilities across complex domains.
Okay, those are solid numbers. And what about our deep dive focus model, the Qwen3 30B A3B? How does its performance compare, given its incredible efficiency focus from that MoE architecture?
Right, the 30B MoE. This is where the efficiency story becomes even more compelling. Qwen3 30B A3B achieves comparable performance to its predecessor, QWQ32B.
The older 32B model.
Despite having a smaller overall model size and, critically, utilizing significantly fewer activated parameters, only about 110th of the full model.
Same performance with 110th the active parameter.
Roughly, yes. This highlights the remarkable efficiency gains from its MoE architecture and that strong-to-weak distillation process we discussed. It's essentially delivering similar quality results with a fraction of the computational cost and active memory footprint.
That's an incredible efficiency story. It's almost like getting high-end performance on a budget. But I've seen some intriguing discussions, and particularly on platforms like Hacker News, comparing it to GPT-4. What's the general take there, and what nuances emerge from that comparison?
Yes, the inevitable GPT-4 comparison. It's a nuanced discussion, as you might expect.
It always is.
One user claimed it's basically a GPT-4 level model, specifically referring to the original GPT-4 from March 2023.
Okay, the early GPT-4.
However, others expressed skepticism or suggested it needs robust tool use to compensate for factual recall.
Needs tools for facts. We heard that might be the case.
Right. Implying it's a powerhouse for reasoning and coding when integrated with tools, rather than an encyclopedic knowledge base on its own.
So maybe not great for pub quizzes on its own.
Probably not its strength. This presents a mixed but insightful picture of its perceived intelligence. Strong in reasoning and action, perhaps less of a broad factual knowledge base internally. It suggests its tool integration is really key for its broader utility.
Which raises an important question for these models. Is pure internal factual knowledge as important as the ability to effectively use external knowledge through tools?
That's a great question, a potential paradigm shift. And the official technical report also details its robust multilingual capabilities, backing up the 119 language claim with strong performance across benchmarks like multi-F, include, MMLU, MTAIM 2024, Polymath, and MLogic QA.
So the benchmarks support the multilingual claim.
They do, covering all 119 languages and dialects. It's a significant technical achievement, showing its broad applicability globally, despite maybe some specific user edge cases we'll touch on later.
Okay. That distinction between internal knowledge and tool use really shifts the paradigm from an AI being an encyclopedia to being an intelligent agent capable of taking action and leveraging external information.
Well put.
Beyond benchmarks, what are real-world users experiencing, especially regarding speed and local deployment? This is what most people have been waiting for, right? The model you can actually run.
Precisely. This model is gaining immense popularity because it can genuinely run on modest gaming rigs. Users are reporting truly lightning-quick speeds.
Give us some examples.
For instance, 12 tokens per second, TS, at Q6 quantization on a mobile RTX 4070 GPU with 12 GB VRAM.
12 teats on a laptop GPU.
Yeah.
Bad.
Even more impressively, a mid-range GPU, like the RTX 4060 Ti with 16 GPU, can hit a remarkable 74 teats using IQ3S quantization.
74 teats. That's flying for local inference on a mid-range card.
It really is. Even for CPU-only inference, users are seeing 15 teats on a Windows 11 machine with an Intel 14900KF.
15 teats on CPU only is very usable.
Definitely.
That's incredibly accessible performance for local setups. And Apple Silicon. They often have different performance characteristics due to their unified memory architecture. How does Qwen3 fare there?
On Apple Silicon, the speeds are equally impressive, if not more so, highlighting the benefits of that unified memory.
Faster on Mac.
Often, yeah. You're looking at around 52 teats on an M4 Pro using 8-bit MLX.
52 teats, solid.
And 60-70 TPs on an M3 Max with Q8 quantization.
60-70 teats on a laptop. Very nice.
Some users even report nearly 100 talks using dual RTX 3090s at a context size of 132K.
Okay, dual 3090s is high-end, but 100 teats is impressive.
Even on a more constrained setup like an A2000, it's an 8GB VRAM laptop GPU. It's hitting a solid 14 talksec with a Llama.
14 teats on just 8 GB VRAM.
And on a Snapdragon X Elite, the new ARM chips for Windows, prompt evaluation reaches almost 30 teats and inference 1820 teats using Q40 in llama.cpp.
So good performance across NVIDIA, Apple, even RAM on Windows.
It speaks to its exceptional optimization for diverse hardware configurations, truly living up to the Lightspeed inference moniker for local setups.
That's truly phenomenal for local deployments.
Yeah.
What about memory footprint for these impressive speeds? How much RAM or VRAM do you actually need to get this running comfortably?
Good question. For comfortable quantized model use on a Mac, you're looking at roughly 30 gigabits of RAM.
30 GB RAM on Mac.
For CPU-only operation, 32 GB of RAM is generally sufficient. A Q6 quantization might require 25 GB of RAM.
Okay, so 32 GB RAM seems like the sweet spot.
With the practical option of offloading layers to the CPU to mitigate VRAM limitations if you're using a GPU.
Or offloading.
And the efficiency of the MOE architecture is underlined here. One user noted, your TS will not drop much because of how MOE operates.
Right, only activating 3 billion parameters.
And in this case, 3B parameters, 8 experts, is still almost nothing, even on CPU only. This design minimizes the impact on speed, even with memory constraints.
And are there any operating system differences in performance, given the varying memory architectures and drivers?
Yes, quite notably. Users have observed that Windows is described as slow WWW in comparison.
Huh. Okay, Windows is slow.
While Linux offers about a 20% speed boost over Windows.
20% faster on Linux.
And Mac's unified memory architecture, where CPU and GPU share the same memory pool, can lead to a remarkable 4-8x faster speeds compared to Windows.
4 to 8 times faster on Mac.
That's what some users are reporting. It's a crucial detail for anyone planning their local deployment, as the choice of OS can dramatically impact practical performance.
That's a huge difference. So Windows users might need to manage their expectations or optimize more heavily, but as with any advanced model, there are always nuances, trade-offs, and sometimes conflicting reports from the community. What are some of the limitations or areas where it might not perform as expected?
You're right, no model is a silver bullet. Some users found it far less accurate helpful than Gemma 3.27b Q4KM in initial tests.
Less helpful than Gemma 327b. Interesting comparison point.
And one user struggled to get working Python Tetris code, where the older QWQ32b succeeded, albeit slowly.
Okay. So maybe some task variability.
And a significant criticism highlighted, which aligns with our earlier discussion about its nature.
The factual knowledge thing.
Exactly. It's terrible, simply terrible at factual knowledge. One user warned, "Don't think about learning anything from it, or you will only know hallucinations."
Ouch. Strong words.
This strongly implies the model's core strength is reasoning and coding, not serving as a factual knowledge base. It's a powerful problem solver, but it needs tools to access and verify external facts.
That aligns perfectly with the earlier point about tool use being central to its broader utility. It's a powerful reasoning engine that uses tools for facts, rather than being the factual source itself.
Seems to be the case.
What about those broad multilingual claims? Are there any discrepancies in user experience there? We saw the benchmarks were good.
Intriguingly, one user claimed failure to be multilingual, which directly contrasts with the official claims of 119 language support and those extensive multilingual benchmarks we mentioned.
That's a direct contradiction.
It is. This is a point that raises an important question for further understanding whether user experience in specific, perhaps more niche scenarios matches the broad benchmark claims, or if there are particular edge cases or complexities in multilingual usage that aren't fully captured by general benchmarks. Needs more investigation, probably.
Yeah, maybe specific language pairs or tasks. And finally, what about the trade-off in its specialized versus general performance? Does trying to make it good at everything dilute its peak performance in specific areas?
Yes, the technical report reveals an intriguing finding that speaks to design philosophy. While thinking mode fusion and general RL enhance overall versatility and breadth of application,
Making it a good all-rounder.
performance in thinking mode can actually decrease for certain challenging, highly specialized tasks, like AB24 and live code bench.
So it got slightly worse at the really hard stuff after the general RL stage.
Potentially, yes. This suggests a strategic trade-off made to enhance the model's broader applicability and general usefulness, potentially at the cost of absolute peak performance in very niche, difficult scenarios.
Optimizing for the common case, maybe.
It's a design decision to optimize for a well-rounded model rather than absolute top-tier performance on every single specialized benchmark.
That's a really important nuance. It seems like they prioritized a versatile, accessible model rather than absolute maximum performance in every corner. That leads us perfectly into the practicalities of running and fine-tuning Qwen3 for developers. After all this impressive technical detail, how do you actually get your hands on it and make it sing?
All right, let's get practical.
So after all that technical deep dive into its architecture, training, and performance, how did developers actually get their hands on Qwen3 and make it sing? Let's start with effortless local deployment. What's the accessibility like for someone wanting to run this on their own machine?
The good news is that Qwen3 models are designed for broad compatibility with popular local inference applications. We're talking about tools like Llama, LM Studio, MLX-LM, Llama.cpc, and K-transformers.
All the usual suspects.
Pretty much. This widespread support makes it incredibly accessible for developers and enthusiasts to run these powerful models right on their own machines, often with just a few commands.
That's fantastic. For developers looking to get started quickly with Python, what's the quick start process like? Is there a straightforward snippet they can use? And are there any immediate gotchas to watch out for?
Absolutely. The Hugging Face documentation provides a straightforward Python code snippet for generating content using the Transformers library, which is, the de facto standard.
Transformers library, yep.
It's typically a simple auto model for causal LM from pre-train call. However, there's a crucial detail that can trip people up.
Uh-oh. What is it?
You will encounter a key error, Qwen3mo, if you're using Transformers versions older than 4.51.0.
Need the latest Transformers.
Yes, updating to the latest version of the library is an absolute must to avoid common frustrations. It needs explicit support for this MOE architecture.
That's a good heads up to avoid unnecessary debugging. And what if a user encounters an out-of-memory OAM issue, which can often happen when dealing with larger models or trying to use very long contexts on consumer hardware?
Yeah, OO errors are common. If you encounter them, the primary recommendation is to reduce the context length to a shorter value, maybe 32,768 tokens, or even lower if needed.
Dial back the context.
While Qwen3 has truly impressive long context capabilities, managing memory is still key for local inference, especially on systems with limited VRAM. You can often still get great results with a shorter context if your hardware is constrained.
Great practical advice. Once it's running, how do you optimize the settings for inference to get the best performance for different types of queries? Are there recommended sampling parameters, especially considering its distinct thinking and non-thinking modes?
Yes, Qwen provides officially recommended sampling parameters to achieve optimal performance for each mode.
Okay, what are they?
For non-thinking mode, where you want fast, direct responses, they suggest temperature 0.7, top 0.8, top K20, and a repetition penalty 1.05.
A bit more constrained, lower top.
Right. This encourages focused, less explorative generation. For thinking mode, where you want more deliberate reasoning and broader exploration of possibilities,
Yeah.
the recommendations are temperature 0.6, min P 0.0, though they note 0.01 often works well, and llama.cpp defaults to 0.1, so maybe some flexibility there.
Okay, lower tempo.
Top 0.95 and top K20.
Higher top for thinking mode. Lets it explore more.
Exactly. The slightly lower temperature but higher top in thinking mode allow for more creativity and exploration during its internal thought process.
Those subtle differences in temperature and top EI can make a lot of sense for encouraging different types of outputs. And what about the maximum output length? Is there a recommended setting to ensure adequate response generation for complex tasks?
They recommend an output length of 65,536 tokens for most queries.
65K output length. Pretty generous.
It is. It ensures adequate response generation, especially when dealing with complex tasks, multi-step agentic outputs, or longer code outputs, allowing the model sufficient space to fully articulate its thoughts and solutions.
So it's not just about getting it to run, but running it well and ensuring it has enough room to express itself. Beyond just inference, many developers will want to fine-tune these models for their specific use cases or proprietary data sets. What's the story with advanced fine-tuning, especially with tools like Unsloth?
Unsloth. Yeah, Unsloth plays a significant, almost transformative role in Qwen3 fine-tuning. It offers dynamic 2.0 quantizations.
Dynamic quantization.
Yeah, which delivers state-of-the-art 5-shot MMLU and KL divergence performance with minimal accuracy loss during quantization for fine-tuning.
Okay, so better quantized fine-tuning.
The practical benefits are substantial. Unsloth makes fine-tuning 2x faster, uses 70% less VRAM, and supports 8x longer context lengths during fine-tuning.
Whoa. 2x faster, 70% less VRAM, 8x longer context? That's huge.
It really is. A compelling example is that Qwen3 14B can comfortably fit in a Google Colab instance with a 16 GB VRAM Tesla T4 GPU using Unsloth.
Fine-tuning a 14B model on a free Colab T4. That's impressive accessibility.
It dramatically lowers the barrier to entry for fine-tuning, making it accessible even on cloud instances or consumer-grade GPUs.
That's an incredible efficiency boost for fine-tuning. It makes customized models far more attainable. Are there any special considerations for fine-tuning the MOE models like Qwen3 30B A3B, given their unique architecture?
Yes, there are some specific nuances for MOE fine-tuning with Unsloth. The Qwen3 30B A3B model, for instance, operates on just 17.5 GB VRAM with Unsloth for fine-tuning.
17.5 GB VRAM for fine-tuning a 30B MOE model.
Wow! Which is remarkably low. A critical detail is that the router layer, which directs tokens to experts, is disabled by default for MOE fine-tuning.
Don't fine-tune the router. Why?
It's often not ideal to fine-tune it directly without very specialized data or techniques. It can destabilize things.
Okay, leave the router alone by default.
Also, users must employ fast model instead of fast language model in Unsloth due to current technical limitations in handling 4-bit BNB MOE models directly with the fast language model class.
Use fast model, not fast language model for 4-bit MOE.
Got it. It's a specific technical point, but important for those diving in.
That's a deep technical point that developers diving into fine-tuning will definitely appreciate. What about the kind of data you should use for fine-tuning to get the best results, especially if you want to retain its reasoning capabilities?
Dataset considerations are absolutely crucial, especially with that thinking reasoning ability. Using a dataset composed solely of non-reasoning data might inadvertently impact the model's carefully trained reasoning ability. It could forget how to think.
Catastrophic forgetting.
Yeah. The recommendation is a mixed dataset. Maybe 75% reasoning-focused examples and 25% non-reasoning examples to optimally retain its core reasoning capabilities while enhancing general performance for specific use cases.
Mix the data to keep it smart. Makes sense.
They also mention the availability of advanced GRPO. That's the reinforcement learning technique again.
GRPO for fine-tuning too.
Yes, GRPO notebooks for fine-tuning, which include features like a proximity-based reward function and custom template support, allowing for highly targeted behaviors shaping beyond simple SFT.
Very advanced options available. It sounds like a lot of thought has gone into guiding developers on how to best leverage these models, from quick inference to highly customized fine-tuning. Let's talk about strategic memory and performance management, especially for those trying to push the limits on their hardware. What are the general guidelines for getting the best out of it?
For optimal inference speeds, say 6 plus tokens per second, the general guidance is that available system memory. Total RAM plus VRAM should ideally match or exceed the model size.
Memory should match model size for top speed.
Ideally, yeah. For example, a 30 GB quantized model might truly benefit from having, say, 150 GB of total system memory to reach its peak throughput by providing ample buffer for context and intermediate computations.
150 GB total memory. Okay, that's quite a bit more than the model size itself.
It is, but that's for peak speed. It's important to acknowledge that running with less total memory is certainly possible, but it will likely lead to slower inference speeds as the system has to swap data in and out more frequently.
So you can run it with less, but you might not get the blazing fast speeds if your memory is a bottleneck. What about that trick we heard about earlier, like offloading layers to the CPU to free up VRAM? Does that work well here?
Yes, that's layer offloading, and it's a valuable technique for Qwen3 MOE. Specifically, offloading the experts, the individual MOE components, to the CPU using options like override tensor in Llama CPP
Offload the experts.
can allow larger models to run more comfortably on GPUs with limited VRAM, say 12 GB or 16 GB. While it's noted that this isn't as universally effective as it might be for a completely different architecture like Llama 4, it still offers significant performance gains for Qwen3 MOE by distributing the memory load.
So it helps, maybe just not quite as dramatically as for some other models.
Seems to be the case. It's
Well-
a clever way to utilize available system RAM when GPU VRAM is constrained.
And just to reiterate, because it's such a significant factor for real-world experience, what are those operating system differences, again, for performance? It sounds like it's not a small difference.
It's worth repeating, as it's a critical practical detail. Windows is notably slower for inference, often described as sluggish.
For Windows,
Linux can offer about a 20% speed improvement over Windows, which is substantial.
20% boost on Linux.
But macOS, with its unified memory architecture, can provide a remarkable 4-8x speed increase compared to Windows.
4 to 8 times faster on Mac again.
Wow. This difference in memory management and GPU utilization across operating systems can dramatically impact a developer's practical experience and choice of deployment environment.
That's a clear roadmap for anyone looking to deploy or fine-tune these models, emphasizing that system-level choices matter just as much as model choices. Now, for the final deep dive into what truly sets Qwen3 apart, its thinking mechanism. This is where the magic and a lot of the advanced capability really happens.
Yeah, the thinking part is pretty unique.
Okay, let's zoom in on what truly makes Qwen3 a unique beast in the LLM landscape. Its thinking mechanism. This isn't just a clever marketing term, is it? It's a deeply integrated and fundamental feature of its architecture.
It's absolutely a core architectural innovation and arguably Qwen3's most distinguishing feature. It's the successful integration of both thinking and non-thinking modes into a single, cohesive model.
All in one package.
Right. This is a significant architectural leap beyond previous models. Even their own QWQ32B, which often required separate instances or cumbersome switching between different model configurations to achieve similar dual functionality. Qwen3 represents a truly unified framework for AI behavior within one model.
That's the key. A single model that can adapt its internal process on the fly. So what actually happens internally when it's in thinking mode? How does it work its magic?
In thinking mode, the model generates an explicit think block before producing its final answer.
A literal think tag in the output stream, or internally.
It's generated internally first as part of the sequence before the final user-facing answer. This block serves as its internal planning or chain of thought space.
It's Scratchpad.
Exactly. It's essentially a transparent scratchpad where the model can perform multi-step reasoning, break down complex problems, and sharpen its responses before delivering the final output.
And this actually helps.
Here's where it gets really interesting. Benchmarks consistently show that models utilizing this reasoning trick perform demonstrably better on harder code challenges and complex reasoning tasks.
So the thinking makes it better at hard stuff.
The process of thinking, visible in that internal block, seems key to the improved outcome. It allows for more robust, potentially more explainable, and maybe even debuggable AI agents down the line.
So it's like a person quietly working through a complex problem on paper before giving you the answer, making their thought process visible if you look. That internal thought process is crucial for complex tasks. How does that compare to the non-thinking mode then, What happens when it's trying to be quick and direct?
In contrast, for the non-thinking mode, Qwen3 streamlines its process by skipping those explicit internal thinking steps.
Skips the think block.
Right. It directly generates a final response, behaving much like a normal LLM for straightforward queries. This prioritizes speed and directness without the overhead of internal planning, making it highly efficient for simple questions or conversational turns where deep reasoning isn't required.
That's brilliant for efficiency. It doesn't overthink simple questions. And as a user or developer, how do you tell the model which mode to use? Is it a complicated API call or is it intuitive?
Not complicated at all. It's designed for seamless dynamic mode switching. Users can dynamically switch between modes by simply embedding think or nothing flags within their user prompts or system messages.
Just type think in the prompt.
Essentially, yes. In multi-turn conversations, the model intelligently adheres to the most recent instruction, maintaining context for that mode.
Okay.
For developers using libraries like Transformers or VLLM, this control is also available via an enable thinking true-false parameter in the API calls.
So easy control via prompt or API.
Making it very intuitive across different interaction methods.
That's a very user-friendly interface for such a sophisticated internal mechanism.
Yeah.
And then there's the thinking budget control, which sounds even more granular. How does that work and what interesting behaviors emerge from it?
Right, the budget. This is an innovative feature that allows users to define a specific token budget for the model's internal thinking process.
Limit the thinking time, essentially.
Essentially setting a time or resource limit for its internal deliberation. What's particularly fascinating about this is an emergent property we touched on earlier. The model can generate coherent responses even based on incomplete thinking if its budget is exhausted.
It gives you something even if it runs out of thinking time.
Yes. This enables it to naturally handle intermediate cases, providing flexible control over the balance between reasoning depth and latency. You can tell it, think for X tokens and then just give me what you've got, which is incredibly practical for real-time applications where you might have strict latency constraints.
So it can provide an answer even if it hasn't fully finished its internal thought process. That's incredibly practical for real-time applications where you might need a response quickly.
Is there empirical evidence that this thinking budget actually helps performance? Does more budget equal better answers? Yes, absolutely. The technical report includes clear scaling curves, particularly Figure 2,
Okay, scaling curves.
which demonstrably show a consistent and smooth improvement in Qwen3 235B A22's performance across mathematics, coding, and STEM domains as the allocated thinking budget increases.
More budget, better scores.
Exactly. This empirically validates its effectiveness, showing that allocating more internal thought directly correlates with better results on complex problems. It proves it's not just a theoretical construct, but a measurable, controllable lever for performance.
That's compelling. It highlights that the thinking isn't just a byproduct. It's a measurable, controllable lever for performance that developers can tune.
Precisely.
What a deep dive we've had into the Qwen3 coded models today. To bring it all together, what are the key takeaways from this exploration?
Well, in summary, Qwen3 Coder truly stands out for its impressive blend of high performance, remarkable efficiency, and unparalleled flexibility.
Performance, efficiency, flexibility.
Right. This is all powered by its innovative mixture of experts architecture and those unique thinking and non-thinking modes we discussed. It truly delivers robust capabilities across agentic coding, complex mathematics, and broad multilingual tasks.
Positioning it as a significant advancement for locally deployable AI models.
Exactly. The efficiency gains, especially with the 30B A3B variant, are a major step forward for making advanced AI accessible on consumer hardware.
Absolutely. The ability to switch dynamically between a deep reasoning mode and a fast direct response mode within a single model, coupled with that adaptable thinking budget, is a real game changer. It means you get the best of both worlds, tailored to the task at hand, without needing to manage multiple models, and that's incredibly empowering for developers and users.
And the multi-stage training process.
Oh,
Now, from massive data scale and diverse language coverage to targeted reinforcement learning and strong-to-weak distillation, it's a testament to the sophisticated engineering behind these models.
a real blueprint for building intelligent and incredibly efficient AI.
I think so.
Indeed. We've seen how it excels in agentic coding, with powerful tool calling capabilities and robust support for real-world platforms, and how its performance benchmarks place it competitively with some of the leading proprietary models.
Narrowing the gap.
And the user experiences confirm its lightning-quick speed and efficiency on everything from high-end GPUs to consumer-grade laptops and even Apple Silicon. It really is delivering on the promise of local, powerful AI.
While there are nuances, of course, like its noted weakness in factual recall when not using tools.
Right, the factual knowledge caveat.
And the strategic trade-off for specialized performance in favor of broader versatility, its strengths in reasoning, code generation, and execution-driven tasks are undeniable.
And the practical guides for running and fine-tuning also highlight how accessible this power is becoming.
Democratizing advanced AI for a wider audience, as we said at the start.
So let's leave you, our listener, with this provocative thought. Qwen3 aims for continuous self-improvement in its coding agents by learning and refining its processes from environmental feedback. What fascinating implications does this hold for the future of human-AI collaboration in software development?
Self-improving tools.
Could it free up human productivity for even more abstract creative challenges? And how might we prepare for a world where our tools can not only perform complex tasks, but also proactively refine themselves?
That's a profound question that hints at a future where AI isn't just a static helper, but an evolving, adaptive partner. It's something to really think about.
Definitely.
We encourage you to delve deeper, perhaps by exploring the official technical reports from the Qwen team, or even trying out the Qwen3 models yourselves. The open source nature makes such experimentation possible for everyone.
Thanks for joining us on this deep dive. We hope you feel much more informed and perhaps even a little inspired by the technical marvels of Qwen3.
Hope it was useful.
Until next time, keep digging into what fascinates you.